Okay, well, I see you know your way around a P-133.
I do. Oh, yeah.
Please be careful, sir.
Oh, I guess you wouldn't want me doing this, huh? Oh, yeah!
Please don't.
Oh! Missed it!
Hey everyone, thanks for watching that fun clip starring the infamous Paul Blart Mall Cop. Now that we have caught your interest, we're going to talk about how these sweet moves are possible through the dynamics and control of a Segway. For those who do not know what a Segway is, it is a two-wheeled personal transportation device invented in 2001. Its main focus is to self-balance. Since its original conception, the Segway technology has been expanded to include hoverboards and other self-balancing devices.
For the dynamics of the system, dynamics of an inverted pendulum were used to solve for the dynamics of a Segway. The inverted pendulum system is an example commonly found in control system textbooks. Its popularity derives partly from the fact that it is unstable without control, meaning that the pendulum will simply fall over if the cart isn't moved to balance it. Additionally, the dynamics of the system are nonlinear. The objective is to balance the system by applying force to the cart that the pendulum is attached to. Similarly, in a Segway, the user holds the rod at an angle theta. The Segway wants to return to the upright equilibrium position and therefore generates a response torque which moves the Segway forward. Equations 5 and 6 are the governing equations of motion and were found by substituting the equations from the free body diagram. Since the analysis of design and control techniques apply only to linear systems, the equations need to be linearized. The datum can be set so that the equilibrium point rests at theta equals pi. Phi represents the deviation of the pendulum's position from equilibrium. Small linear approximations are used to get equations 7 and 8.
The Segway is a continuous system. Measurements are continuously made to check the angle of which the Segway is at and the speed it is traveling at. These measurements are sent into the balance controller, which then sends calculations into a movement controller to achieve the desired torque to rotate the wheels. The balance controller has three inputs: theta, angular velocity, and transverse velocity. These inputs are then outputted as angular velocity, angular acceleration, and transverse acceleration. The movement controller has three inputs and one output. The inputs are angular velocity, angular acceleration, and transverse acceleration. The output is then the torque needed to move the wheels. A single iteration of the control loop can be seen here. The loop begins with measurements, and the result is a motor movement. This loop is then repeated continuously to make the Segway operate.
The system uses a proportional integral derivative controller, also known as a PID, as the control loop feedback mechanism. The PID continuously calculates an error as the difference between a desired set point and a measured process variable and applies a correction. The PID algorithm calculates the error between the angle theta and the equilibrium position and outputs the torque required to maintain balance and not tip over. This graph shows that given an initial theta change, the system responds by moving the theta and theta dot to 0 and outputs a constant velocity. This graph shows that given a continual theta change, the system responds by increasing the velocity.
The Segway is a stable device under normal use. When the rider boards the Segway, the device starts within a delta region where the device is upright. As long as the Segway does not tip over, then any perturbations by the user will bring the device out of delta but within epsilon. The Segway controllers will then bring the device back into the delta region. In conclusion, the Segway is made possible by dynamics and control through linearized equations of motion. The system is a continuous one that has two controllers, balance and movement. The controllers use a PID subcontroller within them, and the result is a stable system.